I'd like to introduce Bob Smith from the Air Force, and he's incredibly famous. If any of you ever saw the picture where a Air Force jet came down and put a missile down a turret of a tank, which changed how bombing occurred by now guided missiles as opposed to just falling out of trajectory. He did the ship. He shot it. So this is Bob Smith, and his talk will be on assuring sufficient number of Deuterons reside in excited bands.
Thank you. I'd like to thank Mitchell and Peter and the committee for inviting me, and my co-author, Tanya Kujakova, who inherited a lot of the books and papers of Talbot and Scott Chubb. So she had a lot of questions on it, and that's how I got to know her. And she's helped with this paper immensely. I'd like to talk about a new mechanism. I don't know where Peter is. Oh, there he is. When we were out at Missouri, Peter told me that he had reviewed Talbot's model of cold fusion, and he says, I didn't see any mechanism to get the deuterons into the band state. He said, I have no known mechanism to do that. And I said, well, there must be one. And so when I got back to Virginia, Tanya and I laid out a plan to try to determine what that mechanism might be, or maybe it's more than one mechanism. So this issue came up, is it one mechanism or many? I said the other day it's many, and I'm going to try to explain why I think it's many. We're looking at the regions of interest that, oh, I killed the power. How'd they do that?
What are the buttons on the blank screen?
Oh, there it is. But I got all that other stuff. Okay. These are the regions that Mitchell and I think George Miley had something to do with that chart, and others. And regions 1 and 2 have normally been used by what I call particle physics, not unlike John was talking about and others. I'm going to concentrate on this talk on areas like, let me get the laser working here. Region 3 here, the work of Arata, I think is extremely important in moving out that way. And I think if new mechanisms like I'm going to discuss are used, that we would have a region 4, maybe a region 5 out in here. Because that's where we have to be if we're going to be competitive for systems that would be used by government agencies such as the Department of Defense, NASA. So I'm going to continue with the fact that we looked very carefully over the Chubb's papers, and we went through as many of them as we could find. I had several in my office. I had the fortune of working with Scott and Talbot for about 17 years, so Tanya and I are probably the only two people still alive that know pretty much what they were thinking and why they were thinking that way and so forth like that. And it would be a waste if I didn't explain to you some of the things I think are valuable on the work they did. One of those is that I asked Talbot one day over at Sochi, Russia, what new physics did you bring to the table here? He says, one simple thing. And I said, what do you mean, just one simple thing? He says, yes. He says, in the Schrodinger equation, there's a Coulomb repulsion term. Peter showed it yesterday. E squared over R12, absolute value. And he says that you got to add in cell to the denominator. I said, that's it? Why is that? He said, because that is the one place where you connect the lattice, and this is what this place is called, lattice-assisted nuclear reactions, right? That's where the lattice assistance comes into the Schrodinger equation when you're in the band state. So I said, well, why is that? And he says, well, when in cell, which is equal to the total number of cells in that crystal. And by the way, these are quantum mechanical cells, Dr. Fisher, because I think you got to get into quantum mechanics to explain some of the things that are happening, even though I'm more of a realist myself and like sim analysis and all that. So I call that the real world, and I call quantum mechanics and wave equations and that sort of thing the imaginary world, but it's a little bit like electrical engineering has A plus BI, you know, and they always do stuff in the imaginary plane, and I wonder why it's real, you know, but they do it. And I'm sure Peter, being a professor of electrical engineering, knows all about that. Well, I'm going on here, and we studied many books on solid state physics, band state physics, statistical physics, chemistry, and I think the reason why we don't know too much about it, it seems very complicated, and you got to read a lot of books to get a flavor for things. But one of the things that came out loud and clear was almost every book, and I was in libraries where there was just rows and rows of physics review letters on solid state physics, band state physics, and every one I picked up had some reference to Felix Bloch, who seemed to know more about the Schrodinger equation than any 10 guys, right? So the Chubbs referenced Bloch a lot. Now I know why, because he's an expert in Schrodinger equation. I'm going to talk more about that. The Chubbs also referenced R. Ninneman, who is a Finnish professor at University of I think Helsinki is in Finland, and his associates. And some of the comments and statements that were in the, oh yes, thanks. View graphs are something you got to have, but like some of the speakers before me, they really tell you what they want to tell you, and if the charts match it, it's a good thing, right? Anyhow, Ninneman and his associates looked very carefully at band state theory. And one of the key things about it was 99.9% of the discussions were about electrons only. And so a lot of the theories are resulting in electron discussion. Not much discussion on positive ions like deuterons. And Peter pointed out to me the importance of the weight. So as I'm reading these documents, I was very careful to note whether they were talking about the weight of a deuteron versus the weight of a proton versus the weight of a hydrogen versus the weight of an electron and that sort of thing. And I found that they like the weight of a deuteron better than any of the lighter ones because they say it acts like a particle and can be transported into the band states, higher band states than they're already in. And by that, I want to point out that that they when the deuterons are in the potential well, at the lowest part of the potential well, they're vibrating a little bit like Vladimir pointed out. He showed little bands in there. And those bands may be very low energy, but they are in the band state even when they're trapped with minimum energy. But as you excite them up higher and higher, the bandwidths get wider. And that's one of the characteristics of the band states. As the temperature goes up, the band gets wider. And it's also true that they say that when the band gets higher pressure on it, it also gets wider. So as you're going up in the potential well, when it gets up to the level where tunneling can occur, and it may cause a fusion in the adjacent potential wells. But these adjacent potential wells, those fusions are of relatively low probability compared with if you can get the deuterons into the ion band state. So I will talk more about that. Also, another point that this solid state crowd says is that the deuterons, when they're in the potential wells, they're in a localized state, but the ones that are more useful in our purpose of being transported into the ion band state are in the delocalized state. And I'm going to show this. Well, I just covered that one, and I didn't mention that. On this particular point right here, metals plated on the surface of the lattice could be the medium for a band state outside of the host lattice. A lot of discussions that I read about were band states within the crystal and outside the crystal. And I got to thinking, well, maybe that's what Dennis Cravens and Dennis Letts were doing when they put that gold, they plated that gold on there and then they hit it with a laser and caused a lot more deuterons to jump into the band state. And so their graph went up. I've seen that graph on 2 or 3 charts, but I think there's a good possibility that that's why those increases are occurring. The new mechanism must include ways to remove the heat of fusion to prevent melting and quenching of the host lattice. Very important. And I was thinking the other day when you were giving your talk about having an avalanche in your reactions, that what may be occurring is that if they're occurring in the band state, and as the quenching, the volcanoes, the pits, and all these things that you've been seeing on a lot of people's charts, you can't have any of those in a reactor because it would avalanche down once it got below the band state minimum energy. It could just drop back into the lattice and avalanche all the way down there. Now, why do you want deuterons in the band state? Is because they have a wave nature when they get into the band state. They act like what Chubbs call quasi-particles. Is they use the duality principle and say, well, when you're at that high a level, you're in a wave state like the Schrodinger equation. I think I've covered some of these points already. I can't cover everything in my time allotted, but as we get into the wave states, here's Felix Bloch. What you want to do is you want to get one deuteron into the band state and then a second one, and then, as Dr. Talbot Chubb said, in 10 to the minus 22 seconds, if the Coulomb barrier is totally overcome, they'll fuse immediately with another one by their waves overlapping. And then you get two, let me see any shock there. Oh, yeah. You get one a D plus and another D plus. That yields a AG4 plus plus wave plus 23.8 MeV. That's what you want, and you want it with a high probability. How do you get a high probability? You got to have a crystal lattice to assist this reaction. Isn't that a neat combination? Because that's the title of this conference: Lattice Assisted Cold Fusion Reactions. And the way you get that is you put in the denominator of the Schrodinger equation Coulomb repulsion term the number of in cell, which is the total number of cells at the crystal. So I didn't have time to write down all the Hamiltonians and so forth, but I found this chart which I could talk to. There's your potential well type drawing that a lot of you have seen, and when they're in here, they're in the band state and then in the band state. But notice there's where the atoms are. And if you would say that's the surface of the material, then right below it you might have another row, and it would maybe interfere and so forth. And in each one of these, you see there's the row and there's the row of atoms. This is the outermost. Here's your Schrodinger equation, the wave equation. But notice this key one here. This is the Bloch wave. And I'm trying to think of a good word that explains why it's different from this one. This is the total Fourier series expansion of the Schrodinger equation that includes the special cases of Bloch. Okay? Now, I remember in math that Fourier series and boundary value problems was a tough course for me. So I'm not going to try to explain to you why he's able to do that, but I noticed in several places that when Bloch drew the Schrodinger equation, he used hash marks. And I don't know whether I call this truncating the Schrodinger equation or whether or not it's something that he's doing to terms. It never really explained exactly why he put hash marks on it, but as you see, he certainly brought in the element of periodic order. So what that amounts to is, if you see, there's the surface of the material right there, but you notice that these waves are inside the lattice and they're also outside the lattice. Well, that means you've got band state throughout the crystal to some degree. No matter what temperature is at or what pressure it's at, you've got it inside the crystal. But there are key characteristics about having a periodic order here, because this wave is propagating over this boundary and that boundary, And that's in X, Y, and Z. It's in 3 dimensions, not just 2 dimensions. So I know Peter was making the argument that it's not 3-dimensional. Well, I think it is, and I'm going to show you something else that leads me to think how we can take advantage of the fact that it is in 3 dimensions. Okay, go on. This next chart here, I showed here back in 2011. This is where we have to get. We got to get out of the laboratory world and into the real world of building power plants. Now, Rossi and Tekefalon, I can't say his name right. They're making a stab at it, and I think that's a good thing. But if you recall the Usmar device, when they really took it apart, they found out it was a heat pump. So there's, vulnerabilities of getting out there and trying to sell something that you think is nuclear. It may not be nuclear at all, as was pointed out here in our previous talk. May not be nuclear, but we are definitely a nuclear thing because we've got wave function overlap in the ion band state. And by the way, there are electrons, blocked electrons in the band state too, and they could be screening electrons like Peter says is important. But once that HE++ wave that overlaps picks up one blocked electron, Dr. Chubb told me the system cascades downward into a helium atom, picks up both electrons and becomes an atom, and we'll try to find a location that's vacant in the lattice, back in the lattice, back down below the ion band state, or it may be a delocalized deuteron, and it's the delocalized ones that are more important to us than the ones that are trapped. So what I've shown here is a real power plant primary loop. And to explain this a little better, I blew it up a little bit. Back in 2011, I showed these plates with holes in them. And I said, why do you want, somebody say, why do you want holes in there? Well, if you make this a gas-cooled reactor, and by the way, the Department of Defense, NASA, they aren't going to want anything with electrolyte in it. No, ooh, I mean, that's a big statement, because 99% of you are thinking electrolysis and electrolytes, but they freeze. They turn to ice. You can't use them in outer space so well without thermal control, and you're going to spend more on the thermal control than the benefit that you're going to get from electrolyte reactors. So you got to get away from electrolytes to be practical. And if you don't remember anything else I say, remember that. Tatiana said, do you know anything about fractals? And I said, no. She says, well, I have a book on fractals that you ought to look at. So we started looking through other books, and we came up with this one. This is the Menger cube, or Menger sponge, they call it. And it's interesting that it evolves from this pattern up here. If this, whoop, if you look at this pattern, this becomes this, and this becomes this, and then you do that in 3 dimensions, you get this. Now, what I think is very interesting about this compared to the chart I just showed you before, where I was using lasers to drill holes in palladium plates, is that in this particular case, each one, oops, gosh, I keep pushing the wrong button here. I don't know what I did that time. I'm having trouble with this thing, Mitchell.
Looks like.
Okay. If you look carefully at this, it's very symmetrical. And my son Scott, who works at Battelle Columbus Labs, he's their IT wizard out there. He sent me a video about this Menger sponge, and it shows you can peel off one layer at a time if you want, or you can slice the whole thing in half. You can slice it this way, this way, this way, and this video went into all kinds of ways that thing could be sliced. And I said, boy, that's wonder if you could put metal on there with deposition was the thought I went. So I sent him an email back and I said, can you put deposition on all those different layers? And he says, yeah, but he says, what's the latest and greatest is metal printing. And I don't know whether you've heard of metal printing. Brian, did you ever hear of metal printing? Yeah, you told me you did. Well, it's a new technology, and yeah, you can make this a 3D reactor with metal plating. And I said, what's the thinnest you could plate? And he came back with another whole series of things on it. 5 microns is the thinnest they have right now, but that'll probably go down to even thinner. So one of the things that I like about this is that it's manufacturable. So this reactor that we come up with, it's going to be practical to have a core that would power a city or a town or something like. It's going to get the attention of some people with money. They don't take kind interest on laboratory work that has no requirement. And I wanted to say a minute or two on requirements. When I was in the Pentagon, I was controlling $1.6 billion of the president's budget with 47 elements of the budget on that many different things. And people, I would have 100 contractors a week come in to me and say, here's this best thing since sliced bread, this widget here. And I say, who needs it? And they say, well, it's a self-evident truth that the Army, Navy, and Air Force and Marine Corps need it. I'd say, next! And my boss would come out of his office down at the end of the hall as I'm walking him out to the front door, and my boss would say, did Bob just throw you out of his office? And they said, well, yes, he did. And he said, well, is it because you don't have any requirement to sell your device to somebody within the military? And he said, well, that's what he said. He said, well, would you want to come in my office and I explain to you how to get a requirement? And they said, well, sure, So they go in there, and he would explain to them that the average rate of time is 3 years to get a fully documented requirement for anything, from a matchstick to a nuclear reactor, And speed of light, 18 months. So 18 months later, they come back and they say, here's my requirement. And I said, where is it? And they said, bring in the requirement, and they start stacking the paper up, and the paper would be about that high. And about this much of it might even be classified. You can't believe it. It takes that much paperwork to get a requirement signed off by at least 14, policy, controller, secretary, deputy secretary. All these requirements. But without one of those, you're not going to get taxpayers' money of any magnitude whatsoever. Well, you need hundreds of millions to get prototypes built, if you can make them. But if you can make reactors that have a certainty of making the fusions take place in the ion band state without melting, you might be able to do it. So what I have here is umpteen ways to cool that thing. And that's what nobody's talking about too much. They mentioned that you got to cool it. You mentioned you have to cool it, but you don't say how you're going to cool it. See, I'm saying you got to take the deuterium gas and make it the fuel as well as the coolant. And you've got to have it in the primary loop, which is here. And it's got to be in this box right here, the core. If it's in here, you've got to get it around the loop, the primary loop. Here's the reactor core. You got to get it around this loop consistently. And you say, well, won't it just burn up? Well, yeah, in a long time, certainly more than 6 months, we were talking about as a requirement, might be 10 years or 20 years. Depends on the burn-up rate and what power level you're operating at. How much power do we need? Somebody told me I need 10 kilowatts per cubic centimeter. The discussion with Brian, he says, I'm not sure you can get that that much out of it, but Martin Fleischman told me personally over in Marseille, France 10 years ago that he was getting 10 kilowatts per cubic centimeter. So I said, well, I didn't ask him how he got it out, and I think he was getting it out in a weapon, but I don't want to get into that. So here you got ways to cool it. And one way you might want to cool it is, these are squares, but I've seen maybe 20 different designs of these fractional grown devices that they do on this was done on a level 5 computer, which I don't know what a level 4 is or a level 6, but when I saw the word level 5, I had a feeling it was a pretty high level computer did this. But I then saw several devices like this that were circular, where you could put, and this just make believe at this moment that that's circular. You could run a heat pipe right out of there. And what's interesting about heat pipes, Los Alamos lab is Tom still here? I don't think he is. Later? He had to leave, yeah. I was hoping he'd be here because he and Ed Storms and my team from Germantown, for a 4-year period, I was the military assistant to the Department of Energy in Germantown, Maryland. And I had a 23-person crew at Los Alamos to build the space reactor to orbit the Earth and produce power for the SDI, Star Wars type space-based lasers, radars, that kind of thing. So Los Alamos design had a reactor that was symmetrical, and it had heat pipes taking the heat away from the uranium. And unfortunately, somebody showed later on in the design that uranium oxide fuel pellets that were producing the fissions would produce free uranium, and the free uranium would dissolve the walls of the heat pipes, and it killed the design. So, but it triggered by getting out and doing something, and that was with $2 million a year we were able to build a design for the heat pipe reactor. It's called SPAR, Space Power Advanced Reactor. And what it did, though, it got people's interest over on Capitol Hill. So I had to go over there about 3 days a week from morning to night, and based on your talk, Mr. Fisher, I spent many hours tutoring staffers on the Hill in the House Science and Technology Committee and the Armed Services House and the House Armed Services Committee, and then they got me going over to the Senate. And as the word of mouth got around that I could explain to them about why we need space reactors and how they work and stuff like that, my schedule I was going 3 days a week and giving 10 presentations, but I'd always give them 1-on-1 or 1-on-2 no more than 2 people at a time, so that we could, I could understand what they knew about it, where to bring them to the level that they understood it well enough to vote yes when they looked through the budget. Because in the budget, where taxpayer money is involved, you always have 3 to 5 times more projects proposed than dollars available. And if you've ever seen one of these budget books, this the Air Force budget book alone is that thick, 1,100 pages. It has 2 pages of descriptive summary. It has these tasks down the left side, these tasks down the right side. If they don't know what goes on those 2 pages, they go to the next 2 pages. So I taught everybody what those 5 tasks were about and why I needed this many millions of dollars to do them. And then when they came to look at it, oh, I know something about that. And they ended up giving me $45 million, which was a fair amount of money, right? You would all like to have $45 million and start a reactor like I'm talking about, even if it doesn't have that shape. It may come out something else. So that brings up the next point. You got to have a story that's easy to understand. So you can't have 1,000 equations like Vladimir puts up here. He puts 1,000 equations. Their eyes roll back in their heads. They do not know solid state, dense state theory to the point where you've got 15 to 30 minutes with each one of these staffers. You got to get to it really quick. So you say, well, when 2 deuterons get in the band state, they have a 100% probability of fusing. They make a helium-4 wave and 23.8 MeV, and it decays down into helium, which, by the way, is an inert gas, makes clean power, and this gas can join the coolant. So now you got, as this thing is going on, you've got helium and deuterium moving through there. But what is that? It's a gas dynamic problem. And so we got out the gas dynamic books, and sure enough, when you got more than one gas, you can have partial pressures, but the 2 partial pressures act as a single gas. So I want to go to the next chart, which is involving the designs of reactors, and then it will be, you got a little bit more time?
There's more speakers.
I can't hear you.
Have to conclude.
Okay, I got to show you one more thing here that I want to show, and that is these charts. This is the Couchmaker curve, and most reactors have got to be on this curve or the next curve I'm going to show you. And I want to show you some of the parameters involved. You see the temperatures are get up in here. This was done at SRI. And you notice that 1,000 atmosphere, you might have heard that. You might even heard 10,000 atmosphere. I'll show this chart, which is done by Wiseman and Summerall. And it points out here, there's palladium black, that was Arana and Zhang. And I wanted to tell you that the reason that Arana wanted to use palladium black was so you know what the smallest crystals were that would melt. And when he gave a talk at Nagel hosted at NRL about 1996, I think it was, 7 in that time frame. He said that any crystals smaller than 0.4 microns would melt. So I'm just about done here. I wanted to show you this chart because when Rada gave his talk at ICBF 5, he got all kinds of excess heat. But Buzz Aldrin, the astronaut, was there, and he and I and Talbot went to Rada and said, "Do you see any helium?" And he says, "No." I was so excited to get all that excess heat, I didn't worry about whether it made helium or not. So Talbot, in behalf of Buzz Aldrin and myself, asked Rada if he, in his next experiments, would look for excess heat. And I want to show you this historic chart because in December of 1995, December 1995, Rada faxed that chart to Dr. Chubb, and it shows the times go this way. So it shows the deuterium going down and the helium coming up. So with that, I think I covered just about everything that I wanted to cover. Oh, recommendations. I'd like to tell you that I think you have to get, in order to get money to develop prototype reactors, you got to put out design definition studies to various contractors. And the number one contractor I would recommend you put on that list is Atomics International, because they are currently, for 25, 30 years now, have been building high temperature gas cooled reactors. But they have fission iso fuel pellets inside the reactor core. If some of you know about fission reactors, you'll know that those reactors have to contain fission products. So the first level of defense on containing fission products, those iso particles. But if you could make those, replace those with cold fusion crystals, something like I showed on the Fractals, that the rest of the reactor is already there. And to complement that, the University of Oregon, in February 2013, which is just 1 year ago, installed a $4.8 million high temperature gas cooled reactor simulator. And without doing simulation analysis, you're going to be fooling yourself on how much time you're going to spend in the laboratory doing it cut and try. You can't do it. You got to have a computer simulation that has all these parameters. And all those parameters are different for every reactor design. So Peter, by answering your issue of mechanism is that you have to tailor the mechanism to each and every reactor design because it involves so many parameters, and the way to optimize that is with computer simulation. Thank you very much.
Questions, Nick?
I saw he had molten salt.
Which picture?
Yeah. What was your question about the...
Are you using the Menger sponge, metallic Menger sponge, as conductive cooling mechanism? Is that the objective?
No, what I want to do is pass the coolant right through it. Now, this is a gas dynamic problem, and anybody that tells you that gas dynamics aren't tricky, they're fooling yourself, because even if you put heat pipes coming out of the reactor box, the working fluid inside of a heat pipe reaches sonic speeds. I don't know whether you know anything about heat pipes, but they're very interesting. But when you're making 23.8 MeV without any degradation or quenching of the material, which is exactly where I think you're at, is you got to get rid of that heat fast. So heat pipes may be needed, but it brings up the issue of can you stand the pressures that are involved with the gas. If you look at this chart very carefully here, look at these numbers on the left side here. There's 10 atmospheres, 100,000. The Couchmaker curve stopped right here. This curve goes on up, way on up there. Well, when you get those kind of pressures and you're moving it fast, you can get supersonic real fast. Well, you can't have supersonic because you got shock waves and you got all kinds of problems. So it's going to take a combination of things, and nobody's mind is smart enough to integrate all these factors at the same time. So it's got to be in a computer, or you just aren't going to get it done. So the message that I'm trying to give you here today is, unless you make a I'm going to use the word paradigm shift because I've heard a lot of people say it. I don't know exactly what it means, but you need to do a paradigm shift to get out of the laboratories and into the real world of contractors. And I recommend that if you got $2 million from Capitol Hill to put out 400 or 500K design definition studies to, like, General Atomics, General Electric, Westinghouse, for example, and tell them, if you can make a reactor that's radiation free, I tell you, the branching ratios that Peter put out there yesterday, they have such low cross-section capability, but they're bad words. The neutron radiation, gamma radiation, bad words when it comes to getting money, because that says there's radioactivity to deal with. Trust me, you don't need those low cross-sections. You need to get into the high cross-section. There's no radioactivity because the radioactivity is spread out over the boundary of the 3D crystal and not any further. And since it's spread out, there's no concentration of the energy to make a neutron or a gamma. And that's why you see no neutrons in most open reactors.
Thank you for that answer. What I'm trying to add is that if you do a mega sponge, you have a variety of different scale sizes.
Oh, yeah.
Some of those will be resonant structures at infrared. In a mega sponge, it's possible to get those resonant holes close enough so that you generate a surface wave. So in addition to whatever you're trying to do with your heat pipe, there's going to be another mechanism for heat dissipation, which is effectively a metamaterial surface wave traveling essentially at the speed of light.
Not only do you have waves there, you have them in various regions, and these different regions, I liken this to palladium black from a Rada. Rada says I put palladium black in there to see which smallest crystals would survive. And I said, survive what? He says, well, I've got more than 10,000 atmospheres pressure in there. I said, how do you get that with 0.85? He says, 0.85. It's got to be over 100% loading. You got to have a solid electrolytic cell there that's totally crammed with deuterium, and it's like a metal solid, is what he says. And he says it takes 22 days to get that much in there and that high a pressure. So it's not real clear to me how high a pressure we can get in a device like this because of the gas dynamic problems. And people who have studied this say there's problems with high temperature, high volume, mass rate of flow gas dynamic systems. So General Atomics, they're experts on this. All they gotta do is replace their uranium core with a cold fusion core, and we'd have commercial gas-cooled high-temperature reactors.